Hello and welcome back to another series. This series is going to be physics and chemistry, I guess. Um, I guess you could also say science. Like, no, not science. Biology. This is science. Um, I'm not sure if I've done with my math series. I think I'll keep going because there's some stuff in math series which you'll also need in this. This first episode is going to be about the periodic table, though, just in case anyone needs to be helped, and it's going to be about atoms. Just this first few episodes, but it won't be like the one you may have learnt at school. This is more updated. So first we're going to start. This is the periodic table I have. I actually have one of these directly above this computer right now. It's much clearer than this is, and I understand all of it. You probably can't see a lot of it though, but I just copied this and remade it, so I made this part. So this is the up here would be the atomic proton number, just this number. Atomic weight, also known as atomic mass. No, mass number, sorry. Yeah, atomic mass. This is also known as the proton number. I know it as the proton number. Here is its symbol. So, there we go. You can probably see that. Its name will be underneath. Probably can't really see that. Phase, melting point, and boiling point you probably don't need to know. And when it says phase, it just means phase at room temperature. And electron configuration you will need to know. You won't be able to see it though, because it's so small. So I brought myself another periodic table, and I can probably read this out. So this is the periodic table as it stands right now, 2016. And there's the elements, so hydrogen, helium, lithium, beryllium. Then we move over to here, so we go that way, there. Then we do new line, lithium over here, beryllium, new line, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, krypton, rubidium, strontium? Yeah, strontium, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, can't remember that one, palladium, gold, candium, idium, tin, and then I don't know any further. Although I do know this one's xenon, cesium, barium. There's the classic ones like uranium, plutonium, but we'll skip all that. The atomic or proton number is the amount of protons an atom has, and an atom always has the same amount. An atom always has the same number of protons as there are electrons. Atomic weight or atomic mass is the number of protons and neutrons inside an atom. And it's the number of protons, just saying, is that I didn't write this down, but it's the number of protons that determines what atom it is. So in GCSE, you'll get told, in GCSE you'll get told, in atom there are electrons, protons, and neutrons. These are the three subatomic particles that make up an atom. There are even further subatomic particles which make these up, but we won't go into that. An electron's mass is 0, a proton's mass is 1, a neutron's mass is 1, and these masses are measured relative to this, which is why they don't have a unit on them. Otherwise there'd be like 10 to something, negative something, kilograms, or I don't know. But their charges are these. In A level or university, you're told an electron mass is this, a proton mass is this, and a neutron mass is this. But we're not gonna worry too much about this because this will worry us too much. So we're just gonna say a neutron mass is 1. charges are the same, and this is their symbol. So an electron is E minus, a proton is P plus, or sometimes just a P, and a neutron is N0 or N, because there's no point adding the 0. Now atoms, notice how I've highlighted that, and I'll talk about this in another video, have no overall charge because, as I said here, there are the same number of protons there are electrons. So if we have an atom with 16 protons, we'll have 16 of those +1 charges versus, and then it has to have the same amount, 16 times the -1 of electrons, and that just cancels itself out, so then we get an overall charge of 0. Protons, there are electrons. So here is how the electron configuration works up to calcium. And if you need refresher, calcium is this one over here. So that's then all of this, and my mouse has gone weird. Give me the arrow. So that's all of that. So protons and neutrons are in the center, making something called the nucleus. Electrons orbit around the nucleus. This is a picture. Now, we can't see exactly how many protons there are, but we know how many electrons there are. We can see there's 1, 2, 3, 4, 5, 6. We know that this is an atom. There's 6 electrons. There are also 6 protons. And the protons determine what kind of atom it is. So we look at our periodic table and we look at the proton number. And 6 makes carbon, meaning that this is a carbon atom. And to find out the amount of neutrons, we do the weight, which is protons and neutrons, minus the protons. So that way you can cancel out the protons to just get the neutrons. So the weight of carbon is 12 minus 6, which is the amount of protons, equals 6. And sometimes I like to call the carbon the devil's element, because it's got 6 electrons, 6 electrons, 6 protons, 6 neutrons. Just a little joke. But an atom size, like a regular, perhaps, I think it's a hydrogen atom, not quite sure about that though, is about 10 to the power of -10 meters. So then, imagine dividing a meter, so 1 meter, by 10 with 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's how big the atom itself, so all of that is. But like in a hydrogen, basically 99% of the atom is going to be empty space because they don't orbit this close and the nucleus isn't that big. The nucleus is 10 to the power of -14. So now we add 1, 2, 3, 4. So that's how big the nucleus is. And a proton / neutron, because the electron isn't that, has nearly a mass of 0, is that big. So most of an atom is really just empty space. Not a vacuum. Well, I guess you could call it a vacuum. It's more just emptiness, nothingness. But the shell configuration works like this. 2, 8, 8, 2, and you can't move until the next shell to the one you're on is full. So this first shell, this one, has 1, 2, so then you can move to the next shell. So then this one's halfway through, so it would get another 4 to make 8 on it, and then you would move on to the next shell. So along the side here we have the numbers called the period numbers, and they tell you how many energy shells, so how many of these shells it has. So we can see carbon, it's this one. It has only 2 shells, and the group numbers tell you how many electrons are on the outer shell. It doesn't need to tell you how many electrons there are in total, because it actually tells you how many protons there are. No, it doesn't. Sorry, that's a lie. It tells you how many electrons there are on the outer shell. So then, if we just had this, then all you have to do is say, well, it's got 6 protons. No, it's in. Ignore that. It's in group 1, 2, and we're not gonna. It's in group 14, but we're gonna ignore this 1. It's in group 4, meaning that it's got 4 electrons in its outer shell, and it's on its second shell. So that means there's going to be 4 electrons on the second shell, and then we just have to fill in all the other shells up. So that's how it works. So here's a better periodic table that you could probably see. So you can see this one actually has the electron configuration here. The one I have also does, but you can't really see anything. Just ignore all of this about isotopes and half-lives, because we'll do that in another episode. So here is the periodic table, 118 elements. They increment the amount of protons increments by 1 all the time, all the way. And what else? That's just it. Well, not just it, but that's it about the periodic table. Now we're going to start learning about the groups. So here are the alkali metals, and here are the noble gases, and here we're also going to learn about. So first, noble gases. So noble gases have a full outer shell. Ignore hydrogen, it's not part of the noble gases. Nope, sorry. Ignore what I just said now. We'll come back to that in just a second. Noble gases, they have full outer shell because they're in group 0 or group 18, because these lower ones go up to 18 electrons. But we also call them group 0. I call them group 0. That just tells you how many electrons are on the outer shell. So it's got a new shell, but there's nothing on it, so it's like an imaginary shell. And they don't really react, because when an element reacts, it's more about the electrons being shared around, and thrown away and all those kind of things, which we'll learn also about. But they just don't react because they've got a full amount of outer shells and they're perfectly fine with it. This one is called the halogens. Now they're group 17, so that's this one, and they have 1 less than a full outer energy shell. And oh yeah, we call them energy shells, that's their technical name. They are group 7 or group 17. I know them as group 7. I don't want to remember all these 18 numbers. And they're very reactive because they don't have a full shell, but they want a full shell. You can see they're always 1 less. They're missing things. And we're going to ignore this and this. Although this one has been confirmed. So that way they want electrons, and they'll react very violently with other elements and atoms to try and get these electrons. These are the alkalis. They have only one on their outer shell. You can see that. You can't see that, right? Yeah. They are in group 1, and here's what I was trying to tell you about. Ignore hydrogen, because we'll come back to that in just a second. They are group 1, that's just their only name, and they are also very reactive. Now for hydrogen. Here we go. Hydrogen has one in its outer shell. Great! That means you can go with the alkalis. But because its outer energy shell, which is its only energy shell, can only hold 2, that means having 1 also means that it's 1 less. Oh, so now we have a problem. Does it go with alkalis or does it go with halogens? Most people put it with alkalis, but some other periodic tables put it with halogens, but other periodic tables don't actually put it, and this is smart. When they want to explain, where is it? This part here, also this part, they instead just take the hydrogen, take the formatting they've made their periodic table for hydrogen, put it to the side, like over here, and then just have arrows pointing at different parts saying, so this would actually say hydrogen, this would be an H, this would be 1, this would be 1.0007, etc. Phase, all these kind of things, this would be a 1. And they just say, aha, this is what the name's going to be. And this one's going to be the symbol. And all those kind of things. So, that's what it is. So it has no actual group because of that. And that brings us to the end of the video. So, oh, can I write here? Wonder. White, no. Give me white. Nope. So that brings us to the end of the video. Like, subscribe, leave a comment, and yeah, I think I'll see you later in my next video. Bye.